person, but hopefully we'll make up for that at the next Bangalore/India event. Agus is, amongst the many things Agus has done, he's actually built a Ford car, an engine, years ago. And so he's well aware of safety and reliability of hardware systems, software systems, whatnot. But most importantly, he's probably the leading expert in model safety, and probably has spent more time thinking about interpretability and how to make models really work in regulated industry. So without further ado, I'm super excited to watch your talk here all the way across the ocean here. Thanks, Agus.
Thank you so much, Sri. I wish I were there to enjoy dosa and sambar, my favorite meal. But anyway, thank you for the time to be able to share my thought with you today. I'm going to share my slide, and hopefully you can see it. All right. I hope you can see the presentation. So I want to share with you a few from regulated industry. Designing quality machine learning model. When I talk about quality, designing quality, I'm talking about model that will be interpretable, model that is reliable, model that is robust, resilient, and model that is fair. This is a very, very critical characteristic when you deploy model. And I will go through some of the definition and example, what I meant by interpretability, reliability, robustness, resilience, and fair. We'll wrap it up into a in 30 minutes presentation here. So I've been giving a talk on the subject ranging from 30 minutes presentation all the way to 30 hours presentation on this subject. So let's see if I can do it well in the next 30 minutes.
Agus,
so let's start with...
Agus, is it safe to say that reliable, robust, and resilient is not an accident of RRR?
Yeah, this is a 3R concept that I'm pushing as well, right, Sri? So and this is heavily influenced. You mentioned about my experience in designing car engine. I used to be one of the engine design manager for Ford Motor Company. When designing product, we always think about all of this concept, and we design product to be like this. It's not by accident. So when we're talking about machine learning, how can we build this one in? How can we design in? So when we deploy a model, it will have all these characteristics. So this is why the title is designing. It's we want to design this, not only just testing or monitoring. All the ML ops, monitoring, all of those things are good. But we cannot rely on monitoring. We have to bring it up front. We design it with these characteristics. So let me start with that and see why is this challenging in machine learning. I'll start with something that all of you are familiar with, gradient boosting machine. Gradient boosting machine, if you look at the model, is basically the response is output, summation of output of individual tree in the model. So if you look at this in this picture, the first tree, for example, I'm only using very shallow tree here, a depth to tree. So in a depth to tree, you have 4 leaves. So for leaf, you can think of that as dummy variable, as one hot encoded variable, 1010. If the data fall into R1, the R1 will be 1 and the rest will be 0. And that's repeated in all the tree in gradient boosting or in random forest. So when you look at this, basically gradient boosting machine or random forest is basically a linear regression. Linear regression of the terminal leaves. So I put it the equation at the bottom. It's no more than linear regression. All of this machine learning are linear regression. The neural network, the final hidden layer in neural network is linear model. So all the embedding space, all the hidden nodes and in the are the features so that linear model work well as a final stage. Gradient boosting machine, XGBoost are the same thing. Creating feature, one-hot encoded features, and so that linear model, summation of that, will be work really well. So the coefficient of the regression, instead of using least square, using boosting technique. So if you look at the gain table in a gradient boosting machine, you get all those coefficient of the regression. So at the end of the day, all this machine learning is basically gigantic linear model. Because let's say if I have 3 depth 7, I will have 128 leaves, terminal leaves in each tree. I boost it 1,000 times, you will have linear regression with 128,000 variables. So with all of this machine learning, we're dealing with incredibly, very, very large regression model. So when we have very, very large regression model, a marvelous thing happen, an incredible thing happen, just like what you see, what you witness in ChatGPT. So with very, very large regression, incredible thing happen. What happened in that? One of the remarkable world of overly parameterized model are two here. I presented here among many things. One is the phenomena of double descent. So as the model becoming more complex, is my neural network getting bigger? Or as my boosting getting bigger, you will encounter something called double descent. The bias variance trade-off that we learn in statistical learning, which when model more complex, the model will not generalize well, evaporate. So you can have, okay, the model not generalize well, but if you make the model more and more complex, it will perform also well in test data. The more complex the model, the better. So the overfitting concept disappears in very, very large model. It also have that's more in standard boosting, in standard boosting. What more occur, what you can see is the one on the right, benign overfitting. If your learning rate very, very small, if your learning rate very small, you can boost it as many as you want, you will not overfit if the learning rate small enough. So what you see, the blue color here are the bias. As the model more complex, going to the right, number of boosting, the model getting better and better because it fit data very well. The variance, it's increasing, but increasing at very, very slow rate and become constant. So you have benign overfitting. So when you split the data, have training and testing, a more complex model, you run H2O auto ML, it will be better. It will be the best. It will get selected. So the more complex the model will be better. So model becoming bigger and bigger and more complex because that bigger model is a better model. So is it true? This sounds too good to be true. Is there any pitfall on this? So this is what the but that we're going to talk about and how to deal with this. One of the things that the question on that is, can we trust this model? So what I'm talking about here, interpretability, reliability, robustness, and resilience, and later we're going to talk about fairness, are really the foundation of trustworthy machine learning. Can we trust this model? The issue of interpretability. Can we understand this model? Can we understand what this model are, when this model making certain decision, can we understand it? It's very important for model debugging, but also very important when the model when the model is wrong. So we know our model wrong. Model will be wrong. That's why you have your AUC is never equal to 1. So model will be wrong, and we need to understand it through interpretability too. The other aspect that's important is the issue of reliability. Model make prediction. Model make decision. Do we know how confident we are with the decision of the model? It's like ChatGPT. Well, you ask anything, it will give you answer with full confidence. The last time somebody sent it to me, I am a professor at University of Connecticut. I don't know how that can be, but a few months ago, I was a professor at University of Wisconsin. How can that be? I never been financial institution. This model gave very confident answer, overly confidence, and wrong answer. So we need to understand the reliability of the prediction. So, and when we talk about reliability prediction, we talk about confidence interval, confidence prediction. We're talking about uncertainty. So we need to evaluate the model. Where, in what situation, in what condition, in what combination of variable, in what range, where the decision is less reliable. So understanding the uncertainty on the prediction and testing it before we release model in the wild is very important. The issue of robustness, how sensitive the model is to small perturbation of the input, small noise corruption. When we build model, we always clean the data, do all kind of gymnastic on the data, and then build model. You put model in the wild, the data will not be clean and all subjected to different noise observation and all those things. Model, machine learning model, as you will see it later, very fragile, very sensitive to noise corruption. This is why you heard a lot about adversarial robustness, adversarial attack on machine learning, because with small perturbation, the model make wrong decision. The fourth issue is resilience. Resilience is about the world change all the time. We have data drift, we have observation drift. How the model will perform under data drift. Performance degradation when environment, then when the world change. And in financial institution, the economic situation and all of those things change all the time. Customer change. How the model will work under this. So now the excuse is, a lot of people in machine learning say, I need to have a good MLOps so I can retrain my model all the time. Retraining model, if the relationship between Y and X, response and input, completely change, it's the right thing to do. But if you retrain model because of lack of reliability, lack of robustness, lack of resilience, that's problematic. That is like having a car that you have to bring to dealership for repair, for service all the time. That's not how we deploy model in real world, particularly for in the environment of high-stake environment, very in critical environment like banking. So we want to build model that is reliable, robust, and resilient. And if things gone wrong, we understand exactly what happened because of interpretability. So we'll go to that. Here is an example, interpretability, a problem. I took the Taiwan credit data, very famous data. I'm sure all of you are aware about this. And I built neural network model. First model with AUC 0.77, second model with AUC of 0.76. So if I run this through my AutoML, model 1 will get selected. What happened here? So in model 1, look at the chart on the left, second from the top on the left that I put question mark. In there, I plot min-effect plot. I plot a PDP, partial dependent plot, to see the effect of pay to, meaning payment status from 2 months ago. Going to the right is basically if the customer delinquent, customer payment current, make payment 2 months ago, or they are already delinquent from 1 month, delinquent for 2 months, delinquent for 3 months, and so on. The more delinquent, the longer the delinquency, it should be the higher probability of default. The loan will not get paid. But here it is, the effect is the other way around. The more delinquent, it said, the better the customer, the better the probability of customer is going to repay the loan. It doesn't make sense, the model. It's completely bonkers. Yet the AUC is better compared to model that's on the right. So this is a really, really problematic in machine learning, that you can have model that complete nonsense and have better performance that get picked by AutoML. This is why interpretability are so important. So now, how do we do interpretability? We typically do a lot of time, a lot of people, and most people do what we call it post hoc explainability. We apply LIME, SHAP, PDP, permutation feature importance, and so on and so forth. The problem is, with this tool, they are very, very useful, but you have to take it with grain of salt, because all these tools are not exact. All these tools are approximation. That's why they often disagree and conflicting against each other very easily. So when using post hoc explainability to understand model, take it with grain of salt, because that is not the truth. It can be wrong. So how in high-risk application like credit decisioning in bank, we are not allowing people to use this kind of tool, to rely on this kind of tool. You have to build model that inherently interpretable. Let's think about how to build model that inherently interpretable. Let's start with deep neural network. And this one, I'm going to start with the simplest thing, feed-forward neural network, simplest thing. And I would argue that neural network is one of the most interpretable model. And we'll go to that a little bit. And at least locally interpretable, okay? Deep neural network with ReLU, only ReLU. Yeah, ReLU is basically, it's the output will be linear. If positive, it will be thresholded to 0 if the value of a neuron is negative. So what happened with the with ReLU network? Let's look at 2 nodes only. The first layer has 2 nodes. So when you give a data point, node 1 can be activated on, node 2 can be off. If node 1 is on, it's linear model. If node 2 is on and node 1 is off, it's linear model too, from linear equation from node number 2. If both nodes are on, linear and linear, combination of linear still linear. So in deep ReLU network, every point they generate 2 local linear models. We know exactly the linear equation associated with each data point. So I'll give example. So what happened in ReLU is basically, in the first layer, in the example that I gave you in the previous page, it split the region of the data into 4 regions, because can be on and off combination. And for each region is linear model. If it go to the next layer, each region will get split further. Region get split further, and for each region is basically linear model. So what deep ReLU network does is basically doing data partitioning so that locally is a linear model. That's what they are, no more than that. So deep ReLU network is gigantic regression, because you can have a lot of regression equation depending on how many nodes and how deep the layer is. But it is basically local linear model, no more than that. So here's an example with the simple concentric circle from scikit-learn, right? You train neural network with 2 hidden layers, 40 nodes each. You get the AUC to classify, you get AUC 0.93. And when you do it, it produces, in this case, 227 regions. And interestingly enough, 40% of this region only have single sample, and that's not very uncommon in neural network. So neural network has create a lot of partition in the data space, and then for each have linear equation. And the region, unfortunately, some of the region have only one or often zero. So it's not very uncommon, depending on the data size. It can be 80% or more, only have one observation or even zero observation. What happens when it has zero observation? This is, let me go back to this. So let's say I train network and I have training that expose the data, just single layer for now. Think about single layer. Expose the first neuron with data, expose second neuron with data, but never see data where both neurons are on. It will still make a prediction. Even never seen data, right? If the prediction is wrong, because it make it up, we call it hallucination, like in like what people call hallucination, right? If we're producing something that good and makes sense, we call it intelligence. And for ChatGPT, if we use it for something that we do today, when these two hallucination, at worst, it's amusing, it's entertaining. But it can do a bad thing too. That's why today, we're still not successful as well in self-driving car, because hallucination kill. So that's the thing that we have to deal with. We need to control this machinery to be more interpretable and to be more controllable. So one way to do it, how can we do this thing to make it more reliable on this decision? Well, one way is to get more data, collect bigger data, and including some people thinking about fake data, creating synthetic data, train it with fake information to do that, or we do it differently. We control the network. We regularize it. So what happened when we regularize it? Here is an example of regularization. You apply L1 penalty. So the network becomes smaller. The red color on the top left is the size, the number of region, without degrading the performance. So we stop at some level when the number of the region is small enough, but the performance not degrading. So this is an example from very large number of partition into smaller number of partition, so you can see very few linear model. All right. So let me move. This is the same thing in gradient boosting machine, by the way. Yeah. So that's what remarkable thing happened with big model. We can control it. Now, I was talking about locally interpretable model in neural network. How can we make the model globally interpretable? Well, we can use the concept, like we call it as functional ANOVA. So with concept of functional ANOVA, we're going to architect the model to be inherently interpretable. I am building model. The first term is basically people in statistics call it generalized identity model, GAM. So I have nonlinear function GJ with univariate input, single variable. If I stop right there, the model is GAM. My GJ, I can use gradient boosting machine, or I can use neural network to construct the GJ. If I need higher order interaction, let's say two-way interaction, I'm adding term, two variable interaction. And I put a neural network or gradient boosting machine for each of these terms. So this is what people call it, if you use gradient boosting machine, is EBM, explainable boosting machine, or our version is XGP2, basically build gradient boosting with 3 depth 2 only. Because 3 depth 2 split variable with 2 variable only to create nonlinearity or to create two-way interaction. Then the model is inherently interpretable because you can plot them, you can see it, you can have exact explanation. You don't need PDP in this. So in local interpretability, you don't need Lyman Sharp. In this, you don't need PDP. You get exact because we don't have to deal with the problem of what PDP has. Here is an example of pictorially. If it's a use neural network, you can use gradient boosting machine for each module. So you put it one by one, main effect, and then interaction to variable. You can get what we call it GAMI-net for neural network, or GAMI3 or EBM in gradient boosting machine. Let me touch switch quickly because I only have 5 minutes. The issue of reliability. Reliability is about prediction uncertainty. Where the model has find me region in the data, find me condition where the prediction is less uncertain. There are wonderful tools like conformal prediction techniques that's growing very rapidly today that you can apply to any model, any black box model, to give you prediction interval. The point is to find, based on the prediction interval, find region where the interval is the biggest or large, because or unacceptable, because those are regions where the model is weak and need to be fixed or need to be monitored. So this is talking about uncertainty. So even if we don't use uncertainty in production, when you deploy it in production, still very, very important during model development or during model testing to get prediction uncertainty so that we know where the model is weak. We know a region where the residual error has big spread, like you see on the chart on the top left. Okay, robustness test. This is talking about perturbation. If I perturb the input in the testing data, if I inject noise on my testing data set, is the model still going to perform well? And that's important because when you deploy model in production, the noise will be different from the noise in the training data set. The problem that we have with random splitting that we have is we're dealing with the same noise. So when you run AutoML, the result, like on the left, on the chart on the right here, the first point that says 0, 0 is basically I'm not perturbing my testing data. I am using some data, I run my AutoML, I'm trying to get the best result. In this example, XGBoost is the winner, as usual, in tabular data. XGBoost is the winner, based on testing data set. But what happened if the noise changed a little bit? The XGBoost that is the winner, it can crumble very quickly. Here is mean square prediction error. It can crumble very, very quickly. Where other model, in this case is regularized ReLU DNN, like what I showed you before, is relatively flat. When noise changes, it works well because it's well regularized model. So you can do XGBoost too, but well regularized it, less depth, less boosting will help you to have model more robust. So that's the situation here in terms of regularization. Here's an example of XGBoost again. I boost it in a lot, model get better and better. So I don't have C bias variance trade-off. I talk about the benign overfitting at the beginning. What happens if I perturb it? Then it starts showing up. You see that model overfit. So the benign overfitting is not benign anymore. It's actually harmful. Resilience is about model drift. How model perform under drift. Evaluation of this are super, super critical because the data will drift. Most people rely on MLOps to do model monitoring. We should not do that. We should bring it up front during model development, anticipate, and choose model that's more resilient against this drift. So you can perform this kind of testing. I'm about running out of time. Let me pick the last one is about model bias and fairness. Testing model bias and fairness. In the US, discrimination is illegal. So we need model that make positive decision parity. You have equal demographic